All right, so we're doing notes 1.5, chapter 1, section 5. We're talking about parent functions and transformations. The first one that we're going to talk about is the constant function. So that is a horizontal line, y equals some number. And in this case, I put a c for constant. This example is 1, so this would be f of x equals 1. So the slope is 0, it's a horizontal line at positive 1. So f of x equals c. The domain is all real numbers because left to right it goes on forever in both directions. And the range, since it's only that singular y value, this range would be 1 in brackets. It's only including 1. So my example is c. The second parent function is the identity function. You also know this as the linear function. It's identity because f of x equals x. And x is its identity. So it's just a graph with a slope of 1, positive 1, and a y-intercept at 0. The domain is all real numbers, and the range is all real numbers. So our next parent function is the quadratic. The quadratic function. You should know this one very well from Algebra 2. That f of x equals x squared. So we'll do our sketch of this graph. So it's going to 0, 0. We know I'm going to go 1, 1. And then 2 will be at 4. So it'll be up there. And the domain, left to right, goes on forever, so the domain is all real numbers. But the range on this one, it does not go on forever. There is nothing below the x-axis. So our minimum range value is 0. 0 is included because we plug 0 into the function. 0 squared is 0. So we have a bracket, 0 to infinity for the range. And then next, we're going to do the cubic function. Let's get this out of the way. So we have the cubic function. Which is f of x equals x to the third power. Graph that one. I know 1 to the third is still 1, but 2 to the third is 8, so it's going to be very steep after you get past that 1. And then the negative values, a negative x value gives you a negative y value when it's raised to an odd power. So domain, left to right, it's all real numbers. Range, well, since this goes down towards infinity, all y values also, so the range is also all real numbers. Cubic function. And then number 5, we have the square root function. For the square root function, we have f of x equals the square root of x. To graph that, we're going to start at 0. And square root of 1 is 1. We wouldn't really want to use the points square root 2, right? Because that would give us not a nice number. Square root 3, no. Square root 4, yeah, square root 4 is 2, so we would get a nice point there. And then graph it. For the square root function, the domain, it starts at the y-axis and continues to the right. So 0, we have to check, does it include or not include? Well, square root 0 is 0, so that is included. We have a bracket for 0 to infinity for the domain. Same thing for the range. There's nothing below the x-axis, so we start at 0 and go up from there. 0 is included. And you have to be careful with the domain on the square root function, because you want to make sure you're not taking the square root of anything less than 0. If anything less than 0, if you take the square root, we give you an imaginary number, and we cannot graph an imaginary value on our graph. All right, so that was parent function number 5. We have parent function number 6 is going to be the reciprocal function. And I know I'm going through these quickly, but there's a lot to cover. And it should all be review. So next is the reciprocal. All right, so if the identity function is f of x equals x, if we take the reciprocal of that, then we have f of x equals 1 over x. So you also know this to be a rational function. You can call it either. When we graph the reciprocal function, we're just going to estimate. We know we have asymptotes, and we're going to curve towards them. So it would look something like that. So domain here, left to right. So from the left, negative infinity, and the graph goes along until we get to the y-axis. At the y-axis, we have a vertical asymptote that we're not going to touch at 0. So from negative infinity, we're going to continue until we get to 0, but we're not going to include 0 because we have to jump over that. And then there's more graph that starts as soon as 0 ends, so in union with, not including 0, and then the graph goes on to infinity. We also want to do the range. So we start at the bottom. We move from negative infinity going up until we get to the x-axis where there's another asymptote. We're going to jump over that and continue on to infinity, so it looks the same. Negative infinity to 0, we're not including the 0, in union with not including 0 to infinity. Our next parent function is going to be the absolute value function. Absolute value function, f of x, is equal to the absolute value of x. Whenever you do your graphs, you need to make them nice and neat. If they're straight lines, then you need to be making straight lines with a ruler or some sort of straight edge. Don't give crazy wiggly lines. So if you take the identity function, f of x equals x, but all of these negative values down here, since we're doing the absolute value, it means the positive version of that number. So we just take those and we turn them up towards the positive. So we take all those negatives and we make them positive. All the negative y values become positive y values. And it gives us our absolute value function graph. Domain for this one, left to right, it does not stop, so it's all real numbers. Range, well, absolute value gives you positive numbers, so nothing below the x-axis. So from 0, including 0, because it can be 0, to infinity. And then we have number 8. And this one's actually a new one for most of you. The greatest integer function. The greatest integer function, the most common one that we see is the step function. The step function, but officially it's the greatest integer function.
That's interesting. It was the greatest because we liked it.
All right, so on this one, it's a little different. Oh, let's write it first. So f of x equals, we have this new symbol. It's a bracket with an extra line in it, like that, of x. It's the greatest integer function. And it means we're only counting by integers, nothing in between the whole numbers. So we can start with, just go -2, -2. So when x is -2, y is -2, and as x increases, y is going to stay at -2 until you reach the next whole number, -1. Not include that one, and then we jump up here to when x is -1, y is -1. And then the y's stay at -1 until you get to the next x value. And then don't include it, and jump up. Stay at 0 until you get to x is 1. And then when x is 1, you jump up in y values. Stay there until you get to the next x value, and then you jump up to the next y. And then stay at that y value until you get to the next x, and then jump up, and so on and so on. So this is when you're counting, or an example of using this kind of graph to represent data. The example I like is like, you know, you hear the average couple has 2.4 children. Well, you don't have 0.4 children, so it would be 1, 2, so you would be on this 2 children until you have that third child, and then you jump up to 3. So you either have 2 children and then you have 3, but you don't have anything in between there. So this is when you're, or like maybe stays in a hotel room, like you don't pay for partial night, like you either stay the next night or you don't, but you don't have a partial charge. So domain here can be all real numbers. Left to right doesn't stop, but the range, and we're actually going to write, this is also a little different than what we normally do. I'm going to write this in set notation. So use that squiggly bracket. And the range is a y value such that y is an element of, this is curvy capital E, into the set of all integers. So it's z with a double line like the all real numbers are, but it's a Z. And then close the set notation. So I'm going to put notes on that of how you read that, because I know this is new. So the line means such that. The E, the curvy E, means element of. And then this Z with the extra line is the set of all integers. All right.